Hello, welcome to the NPTEL online certification course on deep learning. You remember in the previous class, we have talked about the discriminant functions and we have also seen the decision boundaries. So, when we discussed about the discriminant function and then the decision boundary, we have assumed the vectors representing the objects that follow certain probability density function or certain distribution. And the distribution that we have assumed in this case was a normal distribution. So, it was a multivariate normal distribution. And based on that, using this multivariate normal distribution, under different assumptions of the covariance matrix, we have seen that we can have the discriminant functions which are linear, we can have discriminant functions which are quadratic. And accordingly, when we try to compute the decision boundary between the vectors or the patterns belonging to two different classes, the boundary can be either a linear boundary or the boundary can be a quadratic boundary. That depends upon what type of covariance matrix the distribution exhibits. Now, today we will talk about the linear classifier and we will also talk about the support vector machine. Before talking about the linear classifier and the support vector machine, we will briefly touch upon another two different types of classifiers, which are nearest neighbor classifier and k nearest neighbor or KNN classifier. So, let us first talk about what is nearest neighbor classifier or nearest neighbor rule. So, before going to that, you find that in previous few lectures, when we talked about the discriminant function which leads to the decision boundary between the two different classes, in a particular case that when the covariance matrix of all the different classes are of the form sigma square I. That means, in this case the different components of the vectors were statistically independent and all the components have same variance which is equal to sigma square. So, there the covariance matrix for all the classes are same and which is in the form sigma square I, where this I is an unity matrix. Under this, and when the a priori probability of the classes p omega I was equal to p of omega j, there we found that the decision boundary between the classes omega I and omega j was a linear boundary, and not only that, it was a perpendicular or orthogonal bisector of the vector of the line joining the mean points mu I and mu j. So, if this is mu I and this is mu j, then the line joining mu I and mu j is bisected orthogonally by the decision boundary between these two classes. So, this was one of the case in which I can separate two classes by a linear boundary. And of course, in this case, if p omega I is greater than p omega j, then this decision boundary is shifted towards mu j in the sense that for unknown feature vectors our decision will be biased towards omega I, because p of omega I, the a priori probability p of omega I is greater than p of omega j. In the other case, if p of omega I is less than p of omega j, in that case the decision boundary shifts towards omega I. It remains orthogonal to the line joining omega I and omega j, but it shifts towards omega I, indicating that our decision for unknown feature vectors will be biased in favor of class omega j. So, particularly in this case, when p omega I is equal to p omega j, then my decision boundary is orthogonal bisector of the line joining mu I and mu j, which clearly indicates that if I have an unknown feature vector, say x over here, which I need to classify, this is the mean of the vectors belonging to class omega I, and this is mu j, which is mean of the vectors belonging to class omega j. And here we are assuming that the a priori probabilities p omega I and p omega j, they are equal. That means the classes are equally probable. So, under this situation, when I have this unknown feature vector x over here, which have to be classified, what I am effectively doing is, because this x falls on this side of the boundary, so it is to be classified to class omega I. Or in other words, what I am doing is, I am trying to compute the distance between mu I and x, and I am also computing the distance between mu j and x. And here the distance between mu I and x, which if I represent as d of x mu I, and in other case the distance between x and mu j is d of x mu j, you find that d of x mu I is less than d of x mu j. And that is true for any point x lying on this side of the boundary. And all these cases, this vector will be classified to omega I. So, in other words, the classification rule that I am applying is a minimum distance classification rule, where the distance that you are computing is the Euclidean distance between the unknown vector x and the means of the classes. Let us see the other case, where we have assumed that mu I is of the form mu. That means, the covariance matrix of all the classes are same, but the components of the feature vectors may not be statistically independent. That means, the off diagonal elements of the covariance matrix may be non-zero. So, under that situation, again under the assumption of equal a priori probability, that is p of omega I is equal to p of omega j, we found the decision boundary is bisector of the line joining mu I and mu j, but the decision boundary is no longer orthogonal to the line joining mu I and mu j. So, it is a bisector, but it may not be orthogonal. So, what do we do in this case? Again here, if I have an unknown point x on this side, this unknown point x will be classified to class omega I, because it is falling on the side of mu I. Is it a minimum distance classifier? Yes. Again, in this case, it is a minimum distance classifier, because what we are computing is x minus mu I transpose sigma inverse x minus mu I, and I am also computing x minus mu j transpose sigma inverse x minus mu j. So, if x minus mu I transpose sigma inverse x minus mu I, this is less than x minus mu j transpose sigma inverse x minus mu j, then the point x will be classified to class omega I. And you find that this is also a distance measure, but it is not Euclidean distance anymore, but this distance is what is known as Mahalanobis distance. Okay. And you find that when this covariance matrix sigma is of the form sigma square I, and assuming that sigma square is equal to 1, this Mahalanobis distance will be same as Euclidean distance. So, even in this case, where the covariance matrix sigma I of all the classes is same, but the feature components may not be statistically independent, I still get a minimum distance classifier, but the distance that you compute in this case is not Euclidean distance, but the distance that you have to compute is Mahalanobis distance. Okay. So, with this background, now let me talk about what is meant by nearest neighbor rule or nearest neighbor classification. So, as we said before, that every object or every signal is represented by a vector or feature vectors, whichever way the vectors are computed. It may be computed using some signal processing techniques, or given an image, I can simply represent this image as a vector by simply concatenating the columns of the image. So, if I have an image of size say m by n, I will represent this by a vector having m into n number of components. So, that becomes an m into n dimensional vector. So, once I represent these as vectors, that means the signal, an image or whatever is represented by a point in that vector space or feature space. So, as it is an m into n dimensional vector, so I am defining an m into n dimensional feature space, and every image will be represented by a point in that m into n dimensional feature space. But here I am taking a simplistic view, because I cannot represent an m into n dimensional space on a 2-dimensional plane. So, what I am doing is I am projecting them into 2-dimensional space. So, each of these images that you find in this particular plane, they are nothing but different vectors. So, this image is a vector, this image is a vector. I am simply projecting them into 2-dimensional space x 1, x 2, assuming that x 1, x 2 are the feature vectors. Now, given this, let us see what is a nearest neighbor rule. So, here all these images are the known images. I know what is the class from which this image comes. So, for example, I know I have a lot of images which are birds, I have a lot of images which are cars, I have a lot of images which are dogs. Okay. Now, given an unknown image, this I have to classify, or I have to identify what this image is. You know that all those previous images that we had, those are the training images using which I have to classify this unknown image. So, one of the approach in which this image can be classified is, what I do is I simply take the distance of this unknown image or the vector representing this unknown image from all other images which are known. And once I compute this vector, so if I have say p number of previously known images and I have this unknown image which I want to identify, so I have to compute p number of distances, distance from every other image which we have in my knowledge base, right. And once I do that, after that I find out that which is the image which is nearest to it. So, if you go back to the previous one, you find that probably this is the one which is nearest to this unknown image. So, my classification rule is that whichever image is nearest to it, I identify this unknown image to be the image corresponding to that class. So, over here, as this was the nearest image, so I identify this unknown image to be one of these images. And obviously, in this case you find that your classification is not correct, because the unknown image that I had was the image of a car, whereas my nearest neighbor rule has said that it is the image of a dog, which is obviously incorrect. So, what is the problem in this case? The problem is I am trying to find out which is the nearest known image in my knowledge base that is nearest to this unknown image. So, I am taking my decision based on that nearest image. So, my decision is based on only one vector, and if that vector is an outlier, then obviously my decision is going to be wrong, and that is what has happened in this case. So, an alternative is that instead of considering only one image, if I consider multiple number of images. So, what I will do is I will take multiple number of images. So, if I take k number of nearest images, then it becomes a k nearest neighbor rule. So, in k nearest neighbor rule, what I do is, I have as before all these different vectors or images in my feature space. Again, I have this unknown image. I compute the distances from all the known images, and out of that I consider only few or k number of images which are nearest. And then among this k number of images, I compute a vote, that is whichever class of images is in majority in that k number of images, I consider this unknown image to be classified to that corresponding class. So, in this particular case, you find that out of all these images which are nearest, so all these images which are nearest to this unknown image, I have 2 images which belong to bird, I have 2 images which belong to dog, but I have 1, 2, 3 and 4 images of cars. So, these car images are in majority. So, I classify this unknown image to be one of the car images, and my classification in this case is correct. So, k nearest neighbor rule in general gives better result than nearest neighbor rule, because you are taking decision based on multiple number of images or multiple number of feature vectors, which takes care of the outliers, removal of outliers. So, these nearest neighbor rules are very simple to apply, but what is the drawback? The drawback is, usually in machine learning applications, I have lakhs and lakhs of images given for training. So, whether I want to use nearest neighbor or k nearest neighbor, I have to save all those images in the memory, and while taking decision for an unknown image or for an unknown vector, I have to compute all those lot of distance values, and based on the distance values, I have to take a decision that to which class this unknown image should be classified, and that is obviously computationally extensive. So, the simplest approach is that instead of trying to do this, you try to find out the decision boundaries, which we have also seen earlier. So, given a number of classes, given images belonging to 2 different classes, if I can compute a decision boundary between the 2 classes, then for an unknown image, if that image falls on one side of the boundary, it will be classified to say class omega I. If it falls on other side of the boundary, then it will be classified to class omega j. And for that, once that boundary is computed, I can discard all those training images or the training vectors. What I need to store is simply few number of parameters which identifies or which describes that boundary. So, let us see how this can be done. So, let us assume in this case, let us consider this case, that all these feature vectors, they belong to one class, and these are the feature vectors which belong to another class. So, had we used a nearest neighbor rule and given an unknown feature vector over here, in order to classify this unknown feature vector, I had to compute the distances from all these feature vectors which are known. And then based on these distance values, I had to classify this unknown feature vector to either this class, say omega 1, or this class, say omega 2. But now, what I am doing is, instead of computing those distances or saving all these feature vectors in computer memory, I am trying to find out a boundary between these 2 classes. So, assuming that all these feature vectors are linearly separable, I can separate these 2 classes of feature vectors by a linear boundary. So, in a 2-dimensional case, it will be a straight line. In a 3-dimensional case, it will be a plane. In multi-dimensional case, it will be hyperplane. So, given such a linear boundary, in this 2-dimensional case, you find that the equation of this boundary will be something like a x 1 plus b x 2 plus c is equal to 0. So, the parameters representing this particular straight line are the parameters a, b and c, where we know that a vector a, b is orthogonal to this separating line, to the line, and c represents the position of the line in that two dimensional space. So, if I vary a and b, in that case the orientation of the line will be different, and if I vary c, in that case the position of the line will be different. So, this is what we have in case of a two dimensional space. In case of a multi-dimensional feature vector, the equation will be a x 1 plus b x 2 plus c x 3 plus something like k, that will be equal to 0. So, if I have d dimensional feature vectors, I can write this in the form w I x I, where I varies from 1 to d plus w 0, that equal to 0. So, you remember that this equation is similar to what we had derived earlier, the decision boundary between two different classes using the normal multivariate distribution, which was w transpose x plus w naught, that equal to 0. So, this is same as this when this w transpose x is expanded component wise. So, this is the expression that I get. So, this is the equation of this straight line which, or the plane which separates the feature vectors belonging to two classes omega 1 and omega 2 or omega I and omega j. So, given this, now I can move further. So, what I need to do is, given a set of feature vectors belonging to two different classes and assuming that the feature vectors are linearly separable, I have to find out a separating plane or hyperplane which separates the feature vectors belonging to these two different classes. And the equation of that separating hyperplane is simply of the form w transpose x plus w naught is equal to 0. And you remember that such a plane divides the feature space into two half spaces. One of the half space is positive and the other half space is negative. So, if we say that the feature vectors taken from class omega 1, they belong to the positive half space, and the feature vectors taken from class omega 2, they fall in the negative half space. And using this, once I design such a classifier or such a separating plane, then for an unknown feature vector, say y, if w transpose y plus w naught becomes greater than 0, then we take a decision that w should belong to class omega 1, because y is, sorry, this is y not x, that because y is falling on the positive half space. Whereas, if we find that w transpose y plus w naught becomes negative, it is less than 0, then our decision will be that y should belong to class omega 2. So, what we have is, for all the known samples or the training samples, if the training sample is taken from class omega 1, I should have w transpose x plus w naught greater than 0, when x belongs to class omega 1, and w transpose x plus w naught should be less than 0 when x belongs to class omega 2. So, whichever w weight vectors w and the bias term w naught I choose, that must satisfy these relations, these inequalities for the samples taken from class omega 1 and the samples taken from class omega 2. Right. Now, we find that this particular expression w transpose x plus w naught I can put this in an unified representation in the form that I can write this as A transpose y. How I can do it? I have to append an additional dimension. I have to append any additional dimension into this x. So, if x is of dimension d, I have to append a 1 to this dimension to this x and make it of dimensional d plus 1. So, the way it is done is, suppose it is a d dimensional vector. So, this w transpose t, w is also a d dimensional vector. So, I have w 1, w 2 up to w d, this multiplied by x 1, x 2 up to x d. So, this is the expression which gives me w transpose x plus w naught, this equating to 0 gives me the equation of the separating plane. Now, this equation I can rewrite in the form w 1, w 2, w d, w 0, x 1, x 2, x 3 up to 1, this equal to 0. So, I can call this as A and this as y, right. So, my equation simply becomes equation of the plane as A transpose y equal to 0, where A is w appended by w naught and y is vector x appended by an additional component which is equal to 1. So, I can represent that equation w transpose x plus w naught equal to 0 as w transpose y equal to 0. And as before, if y belongs to class omega 1, I have to have A transpose y greater than 0. If y belongs to class omega 2, I have to have A transpose y less than 0. What I can do is, for all the y which are taken from class omega 2, I simply negate them. So, for them, instead of considering y, if I consider minus y for all y which are taken from class omega 2. And if I do this, then if y is correctly classified by A, I will have simply A transpose y greater than 0, where y, if it is taken from class omega 2, it is negated y. So, given this, I have now uniform criteria of correct classification that A transpose y has to be greater than 0 for all the training samples y, whether they are taken from class omega 1 or they are taken from class omega 2, because for all the y's which are taken from class omega 2, they have been negated. So, my design approach can be that I can start with any A arbitrarily. But if I find, so with this A, I test all the training samples. So, as long as for every training sample A transpose y remains greater than 0, I know this A correctly classifies all those training samples. But if for any training sample I find that A transpose y becomes less than 0, then I know that this y has not been correctly classified, or it has been misclassified by this vector A. So, what I have to do is, in this particular case, this A has to be modified. So, in order to do this, what I can do is, I can compute some sort of error terms. That is, for every vector which is misclassified, I will compute an error. So, the error term, because y will be misclassified if A transpose y is less than 0, I can simply compute the error term as minus A transpose y. So, whenever A transpose y is less than 0, minus A transpose y will have a positive term. So, if I check all the feature vectors, all the training vectors which are misclassified by this A, I collect all of them, compute minus A transpose y for all those feature vectors which are misclassified, and take the sum of all of them, right. So, I compute an error say j, which is equal to minus A transpose y for all y which are misclassified. And j will be equal to 0 if all the samples are correctly classified. So, you find that if I have the misclassified samples, this sum of minus A transpose y is going to be positive. And if all the samples are correctly classified, all the vectors are correctly classified, then the value of j will be equal to 0. So, while designing this A, or while designing the boundary between the linear boundary between two different classes, our approach should be that we should be able to, or we should try to reduce this error term j. Okay. And for that, the kind of approach that can be taken is something like this. So, I have this A, I will put an initial A to be equal to 0, okay. And then gradually in the kth step, I should be able to get a k from A of k minus 1, that is the previous value of A, such that I move from a k plus 1 to a k minus 1 to a k in such a way that this movement will try to reduce the error j a, if I represent the error as a function of a, that when I move from j a k minus 1 to a k, the error a should be reduced. So, we will talk about this more in our next lecture. Thank you.